Hi there, and welcome to my channel. In this question, we are given that the density of a bacteria population in a circular petri dish at a distance r centimeters from the center of the dish is given by an increasing differentiable function f, where f of r is measured in milligrams per square centimeter. And that's important because at some point we will have to interpret the answer. And values of f of r for selected values of r are given in this table above. And question A asks us to use the data in the table to approximate f prime at point 2.25. And let's sketch a little graph here. So let's do, this is f of r, this is r, and there are 2 points here, 2 and 2.5, and this is not up to scale. I just want to make it a little wider. This point here is f of 2. This point here is f of 2.5. And then this function looks something like this. This is increasing function, smooth increasing function because it's differentiable, it's continuous. And so we need to approximate this point is 2.25. The slope of this line, which is tangent to the graph. So we need to approximate the slope of this line, which is exactly equal to the derivative at the point 2.25. And how can we approximate it? We can approximate it given that we have only that information with the slope of this line, which goes through the points f of 2 and f of 25. And the slope of that line we can calculate as per usual formula as rise over r, dy over dx. So then, putting this all together, we get that f prime of 2.25 can be approximated as f of 2.5 minus f of 2 divided by 2.5 minus 2, so rise over r. And plugging in the values, then we can get that f prime at 2.25 is equal to, and from the table above, we can see that the values are at 2.6 and at 2.5 the value is 10. So the equal to 10 minus 6 divided by 2.5 minus 2, which is 4 over 0.5, which is 8. And the units are milligrams per centimeters cubed. And why is that? As we said, the units of the density are milligrams per square centimeter. And so here we differentiate with respect to r, which is also centimeter. So it becomes milligrams per square centimeter per centimeter, or in other words, milligrams per centimeter cubed. And then what is the interpretation of the derivative here? It's the rate of change of the function. So the derivative is the rate of change of the function, rate of change, which means in this case that at radius at r equals 2.25, the density increases by 8 milligrams per centimeters cubed. Let's move on to question B. In part B, we are given that the total mass in milligrams of bacteria in the Petri dish is given by the integral expression, 2 pi, integral from 0 to 4, r, f of r dr. And we need to approximate that integral using a right Riemann sum with the 4 subintervals indicated in the data in the table. Let's again sketch a little graph here. So we have, this is R, and then these points are that we have a 0, 1, 2, 2.5, and then 4. And on the vertical axis, let's actually sketch not f of r, but r times f of r, because that is the expression in the integral. And so r times f of r, looking at the table, this is equal to 0 because r equal to 0. F of r, f of 1 times 1 is equal to f of 1 times 1 is equal to 2. So this point is 2. And this is again, maybe not up to scale. F of 2 times 2 is 6 times 2, which is 12. So let's write this as 12, this point here. And then f of 2.5 times 2.5 is 10 times 2.5, which is 25. So this point is 25. And then f of 4, which is 18 times 4, is equal to 72. So this point here is 72. And so we need to approximate this integral times 2 pi by the right Riemann sum. And the right Riemann sum means that we take the right side of these rectangles. Not the left Riemann sum, not the trapezoidal sum, but the right Riemann sum. So for these rectangles, we take the right side. So for example, for this first rectangle, we take this side as the height of this rectangle. And so the area here for the first rectangle is given, this is A1. This is A1, this is A2, this is A3, and this is A4. A4, the area of those rectangles. So let's calculate those, and that's simple base times height. And so the integral 2 pi, integral from 0 to 4 of r f of r dr is approximately equal to 2 pi times. So for the first, for this is A1 plus A2 plus A3 plus A4. And so this is equal to 2 pi. For the first rectangle, base is 1 times the height is 2, plus for the second rectangle, base is 1, the height is 12, plus for the third, the rectangle, the base is 0.5 and the height is 25. And for the last one, the base is 1.5 and the height is, I believe, 72. Yes, 72. So using the calculator here, we get that this is equal to, this is equal to 269 pi, and then plugging it into the calculator, because we need that value, is equal to 845.088. I plugged in earlier into the calculator. And so this is measured in milligrams, because we are integrating, we find the total mass in milligrams. Let's move on to question C. In this question, we are asked whether the approximation that we found in part B is an overestimate or an underestimate of the total mass of the bacteria in the Petri dish. And so let's look at the derivative of the function under the integral. So we had, the function was r times f of r. So let's look at the derivative. of this function to see whether it's increasing, decreasing, or we can't say anything about it. So differentiating this using the product rule, this is f of r plus r times f prime of r. And note here that f of r, the minimum value here is 1. Then it says that the function is increasing. So this is greater than or equal to 1. R is greater than or equal to 0. This is positive r. And then f prime, because the function is increasing, f prime is positive. So overall, this is greater than 0. So this function in the integral is increasing as well as the function f of r. So as a result, let's just draw a little graph here again. So here is what we have. We have for each one of those rectangles that we had, let's say this is point A, this is point B, and then this is f of A, and this is f of B, which is not the same f of r. It's actually, in our case, this is r times f of r. And this function here is somehow increasing. And we are using as an estimate for this area here, the exact area which lies under the integral. We are using the right Riemann sum, which is this height times the base. And so the overestimation is this region here. So this is the amount that by which we overestimate. Overestimation. So as a result, the answer is that the estimation that we found is in part B is an overestimation of the true value. Let's move on to part D. In this part of the question, we are given the explicit form for the density of bacteria in the Petri dish, which is G of R equals to 2 minus 16 times cosine of 1.57 square root of R cubed. And then the question is, for what value of K between 1 and 4, G of K is equal to the average value of G of R on this interval from 1 to 4. And so let's recall what is the average of the function. Average of the function is for the integral from on the interval a to b is 1 over b minus a times the integral from a to b of the function f of x dx. This is the average. And so in our case here, the average is equal to 1 over the endpoints are 4 minus 1 integral from 1 to 4 of the function g of r, which is 2 minus 16 cosine 1.57 square root of r close parenthesis cubed dr. So we will need to use our calculators and calculate this average. So this average will be some number. And then we need to equal G, find such case that G of K is equal to this average. And so G of K is 2 minus 16 cosine 1.57 square root of K cubed. And then we subtract average that we will calculate, average. And we find such K that this is true. And that will be our answer. So let's pull out our calculators and calculate first the average and then K which corresponds to this equation, second equation. And so let's calculate the average first. And the average is 1 divided by 3 times the integral, definite integral, from 1 to 4 of the function 2 minus 16 times cosine, in parentheses, cosine of the function 1.57 square root of x, close parentheses, cosine to the third power with respect to x. And we are using x here instead of r, it doesn't matter. So let's do the calculation, enter. And the answer is 9.875795. And so let's do the solver and solve that second equation. And we go to mathematics, solver. And our equation is 2 minus 16 in parentheses cosine of the function 1.57 square root of x, close parentheses, close another parentheses, cubed, close parentheses, minus the value that we just found, which is 9.875795. And let's go to the solver, and let's start with the initial value between 1 and 4. So let's start with 2.5 and then do the solving. And the answer is 2.497. So the answer is 2.497 centimeters. And so as we just calculated, the average density on this interval is 9.875795, and this is milligram per centimeter squared. And then K is equal to 2.497, and this is in centimeters. Thank you for watching. If you like this video, please don't forget to click the like button, and also write me your comment in the space below, and subscribe to my channel where you can find more solutions to Calculus AB and Calculus BC problems. And I will see you in the next video.